There is a place where human intuition goes to die, and its name is light. For centuries, we thought we understood it. A beam, a ray, something that travels from here to there. Newton imagined light as tiny particles. Huygens saw it as waves rippling through space. Both were right. Both were catastrophically wrong. What Richard Feynman discovered, or rather what he helped articulate with brutal clarity, is that light behaves in a way so alien to our everyday experience that even now, decades after the theory was confirmed to absurd precision, physics cannot explain why. We can describe what light does with godlike accuracy. We can predict its behavior to 1 part in a trillion. But the deeper question, the why, remains wrapped in a mystery so profound that it shakes the very foundation of what we mean by understanding. Let's begin with something simple. You are in a dark room. You flip a switch. Light floods the space instantly. Common sense says light traveled from the bulb to your eye. A straight line, the shortest path. This is so obvious it barely seems worth stating. But here is the first crack in that certainty. Imagine placing a pane of glass between the bulb and your eye. Some light reflects off the glass back toward the bulb. Some passes through. If you polish the glass to atomic perfection, if you make it absolutely flawless, exactly 4% of the light will reflect, not 3.9, not 4.1. Exactly 4% for a given wavelength. Why 4? What decides which photons, these indivisible packets of light, reflect and which transmit? They are identical. The glass is uniform. There is no hidden variation, no microscopic defect marking some photons for reflection. Yet 4 out of every 100 turn back. The rest go forward. This is not a minor curiosity. It is a window into the abyss. Now make the glass thinner. Not a thick pane, but a thin film, like a soap bubble. Light can now reflect off both the front surface and the back surface. Classical intuition says the 2 reflections should add. If the front reflects 4% and the back reflects 4%, you should get roughly 8% total. But that is not what happens. Depending on the exact thickness of the film, you can get anywhere from 0% reflection to 16%. 0. Total darkness, where there should be light. Change the thickness by a few hundred nanometers, and suddenly you get brilliant reflection, 4 times stronger than expected. This is interference. The light reflecting from the front and the light reflecting from the back are not acting independently. They are conspiring, communicating across the thickness of the film, adding together or canceling each other out with perfect mathematical precision. This pattern repeats as the glass gets thicker. 0 reflection, maximum reflection. 0 maximum, oscillating like a heartbeat for millions of cycles. It is not random. It is exquisitely predictable. But how does the light at the back surface know what the light at the front surface is doing? The only answer that works, the only framework that accurately predicts these wild oscillations, requires abandoning the idea that a photon takes a single path. The photon does not choose between reflecting off the front or the back. It does not pick one route. Instead, in a conceptual leap that defies every classical instinct, the photon simultaneously takes every possible path. It reflects off the front. It penetrates and reflects off the back. It bounces internally multiple times. It even takes absurdly roundabout detours through space. All of these possibilities occur in superposition, and what we observe, the final probability of seeing the photon at a detector, is the result of adding up contributions from every single path. This is the path integral formulation, Feynman's masterpiece, and it is as beautiful as it is baffling. Each possible path is assigned a probability amplitude, a complex number that can be visualized as a tiny arrow with a length and a direction. For paths that are similar, the arrows point in roughly the same direction. They add up constructively, reinforcing each other. For paths that differ significantly, the arrows point in random directions. They cancel out, destructively interfering. In the thin film example, when the thickness is just right, the arrow for the front reflection and the arrow for the back reflection point in exactly opposite directions. They sum to 0. No reflection. When the thickness is different, the arrows align. They add up. Maximum reflection. The mathematics is straightforward once you accept the premise. But the premise is staggering. Light is not localized to one trajectory. It explores reality, sampling every conceivable route simultaneously. And only upon measurement does it collapse into a single observed outcome. This is not metaphor. This is not approximation. This is the literal mechanism by which light, and indeed all quantum particles, navigate the world. The paths you block were contributing, even though no single photon was ever detected on those paths. They are real in the calculation, essential to the outcome, yet invisible to direct observation. Feynman called them virtual paths, and they are as close to magic as physics gets, except the magic is real and the predictions are flawless. This is not metaphor. This is not approximation. This is the literal mechanism by which light, and indeed all quantum particles, navigate the world. You can test it. You can perform experiments that block certain paths, and the interference pattern changes precisely as predicted. The paths you block were contributing, even though no single photon was ever detected on those paths. They are real in the calculation, essential to the outcome, yet invisible to direct observation. Feynman called them virtual paths, and they are as close to magic as physics gets, except the magic is real and the predictions are flawless. Take this further. Why does light reflecting off a mirror obey the simple rule that the angle of incidence equals the angle of reflection? It seems like a fundamental law carved into nature, but it is not. It is an emergent property. When light from a source reaches your eye via a mirror, it can reflect from any point on that mirror. The top edge, the bottom corner, the dead center, everywhere. Each of these reflection points corresponds to a different path, and each path has its own probability amplitude arrow. For most of these paths, especially those far from the center, the arrows point in wildly varying directions. They cancel each other out almost perfectly. But for the path where the angle in equals the angle out, something special happens. For that path and the paths immediately near it, the arrows all point in nearly the same direction. They add up, they reinforce. That region of the mirror dominates the probability. The law of reflection is not a decree. It is a statistical consequence of constructive interference among the myriad quantum paths. You can prove this. If you carefully scratch parts of the mirror to eliminate certain paths, you can create what is called a diffraction grating. Now light reflects at impossible angles, directions where a normal mirror would never send it. Why? Because you have removed the paths that were causing destructive interference. You have sculpted the space of possibilities, and the light obediently follows the new sum of amplitudes. The mirror is not forcing light to obey a law. The light is obeying the cumulative interference of all its possible histories, and the mirror merely shapes which histories contribute. Now here is where Feynman's revelation becomes truly humbling. The entire edifice of the visible world, every color, every glint of sunlight, every shadow, every reflection, reduces to an almost absurdly simple underlying script. There are only two actors in this cosmic play: the photon, the quantum of light; the electron, the quantum of charged matter. And there are only three fundamental actions from which all electromagnetic phenomena arise. A photon travels from point A to point B. An electron travels from point A to point B. An electron emits or absorbs a photon. That is it. Three actions. Everything else, and I mean everything, is just elaborate combinations and repetitions of this trio. The red of a rose. Photons from the sun absorbed by electrons in pigment molecules, then re-emitted at a specific wavelength. The blue of the sky. Sunlight scattered by electrons in air molecules, with shorter blue wavelengths scattered more efficiently. The warmth of sunlight on your skin. Photons absorbed by electrons in your skin cells, transferring energy. Vision itself. Photons entering your eye, absorbed by electrons in retinal proteins, triggering a cascade. It is all photons and electrons, emitting, absorbing, traveling, nothing more. Feynman developed a diagrammatic method to visualize these interactions. For any process, you draw all possible ways it could happen using the three basic actions. Each diagram tells a story. A photon starts here, gets absorbed by an electron. The electron moves, emits another photon, and so on. Each action in the story has a probability amplitude. Multiply the amplitudes for all the steps in one diagram, then add up the amplitudes from all possible diagrams. The final sum gives you the probability of the observed outcome. This is quantum electrodynamics, QED, and it is the most successful theory in the history of science. Its predictions match experiments to a precision that borders on the incomprehensible. Calculating the magnetic moment of the electron, QED predicts a value that agrees with measurement to 12 decimal places. Imagine measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. That is the level of precision we are talking about. But buried in this success is a number that nobody can explain. Every time an electron emits or absorbs a photon, the probability amplitude for that fundamental interaction has a fixed size. That size is approximately 1 divided by 137, or about 0.0073. This number is called the fine structure constant, alpha, and it is one of the most mysterious quantities in all of physics. It sets the strength of the electromagnetic force. It determines how tightly electrons are bound to atoms, the nature of chemistry, the stability of matter. If alpha was slightly larger, atoms would collapse. If it was slightly smaller, they would not bind at all. Life, complexity, everything we know depends on this number having the value it has. Yet we have no idea why it is 1 over 137. We can measure it with staggering precision. We can use it in calculations that predict nature with godlike accuracy. But we cannot derive it from any deeper principle. It is a brute fact of the cosmos, an input to the theory, not an output. Feynman himself was haunted by this. He called it one of the greatest damn mysteries of physics, a number whispered by the universe with no explanation. There is another layer of strangeness. When you calculate the probability for an interaction, you must include diagrams that seem physically absurd. For example, when two electrons repel each other, the standard story is that one emits a photon and the other absorbs it. But to get the right answer, you must also include diagrams where the photon travels faster than light, or backward in time, or has negative energy. These are virtual photons, ephemeral entities that exist only in the intermediate steps of the calculation. They are never directly observed. They violate classical conservation laws. But if you leave them out, the theory fails. The predictions are wrong. Nature requires these impossible intermediate states to produce the correct final result. It is as if reality is allowed to cheat in the middle of a calculation, as long as the books balance at the end. The virtual photons are mathematical ghosts, essential to the machinery but forever hidden from view. They are part of the universe's internal accounting, and we are granted only a glimpse of the final ledger. This brings us to the epistemological cliff. We have a theory that works. It works better than any other theory in science. We can build lasers, design semiconductors, construct MRI machines, and engineer the entire technological foundation of modern civilization on the basis of QED. But we do not understand it. Not in the way we feel we understand a falling apple or a rolling ball. We cannot answer why light takes all paths, why probability emerges from the square of the amplitude, why the fine structure constant is 1 over 137, why only 3 actions, why quantum mechanics is the way it is. These are not gaps we expect to fill with better measurements. They are foundational questions about the nature of reality, and the answers, if they exist, lie beyond our current conceptual reach. Feynman was refreshingly honest about this. He said that nobody understands quantum mechanics. You can learn the rules, you can calculate, you can predict, but the why, the intuitive grasp, the feeling of comprehension, eludes us. The quantum world operates on principles fundamentally alien to the macroscopic world our brains evolved to navigate. We are pattern-recognizing apes trying to decode a universe that does not care about our intuitions. The best we can do is mathematical description. The equations are our map. They tell us where to go, what to expect. But the territory itself, the underlying reality, remains strange and, in some profound sense, unknowable. What Feynman discovered about light, then, is not a comforting explanation. It is a confrontation with the limits of human understanding. We possess a tool of extraordinary power, a framework that predicts the behavior of light and matter with precision that feels almost supernatural. But the price of that power is accepting a picture of reality that is deeply, irreconcilably weird. Light is neither a particle nor a wave. It is something else, something for which we have no adequate classical analogy. It takes all paths. It interferes with itself. It is described by probability amplitudes that live in an abstract mathematical space. The photon you see hitting your eye did not travel a single route. It sampled every possible route, and the one you observe is the outcome of a vast silent conspiracy of interfering possibilities. Physics, at its pinnacle, has not given us certainty. It has given us staggeringly accurate descriptions and a profound, unsettling awareness of how little we truly understand. The light that illuminates your room, the light that carries this message to your screen, the light that warms your face, operates according to rules we can write down but cannot fully grasp. And perhaps that is the deepest lesson. The universe is not obligated to make sense to us. Our job is not to impose our intuitions on nature, but to listen, to calculate, to test, and to accept what nature reveals, however strange it may be. Feynman spent his life doing exactly that, and in the process, he showed us that the mystery of light is not a failure of physics. It is a reminder that reality is richer, stranger, and more beautiful than we ever dared imagine.